everyone. I'm Arham from Sri Venkateshwar College of Engineering, studying in the third semester. I'm here with the concept in mathematics that is called the well-ordering principle. What is the well-ordering principle? Every non-empty set of positive integers contains a least element. Importance: the fundamental in mathematical proofs. It states that every non-empty set of positive integers contains at least one least element. This means that if you have any collection of positive integers, there will always be a smallest number in the collection. Formally, for any non-empty set of S of positive integers, there exists an element such as that is greater than or it is lesser than the element. Foundation for proofs. The well-ordering principle is often used to prove theorems by induction. Set theory. In set theory, the well-ordering principle is closely related to the axiom of choice. In number theory, it is used to prove the results about divisibility of prime numbers and the divisibility in the structure of integers. For instance, it is used in the proof of fundamental theorem of arithmetic, which states that every positive integers can be uniquely factored into prime numbers. It is also used in algorithm design. In computer science, the algorithm design for well-ordering principle is used in proving the correctness of the algorithms. The origins and development, early mentions in the ancient mathematics. Ancient Greek mathematics early reform. The well-ordering principle can be traced back in ancient Greek mathematics, including Euclid, implicitly used in concepts related ordering and minimal elements in their geometric and the number of theoretic works. Medieval and the Renaissance mathematics also had this continued the use of ordering principles, although that is not formed in the manner seen in modern mathematics today. Richard Dedekind made significant contributions in the formalization of well-ordering principle. The diagram illustrating this concept is a well-ordered set, visual representation of axiom of choice, its connection to the well-ordering principle theorem. The timeline is showing key historical milestones of the development in the mathematics for medieval scholars Dedekind and Cantor. The relation to other principles in a detailed content. The well-ordering principle with every non-empty set of positive integers contains a least element. It applies to the set of positive integers and more generally any set that can be well ordered. Zorn's lemma. The definition here says that if every chain totally ordered subset is partially ordered set of upper bound, then the set contains at least one maximal element. It is used in various areas of mathematics, including algebra, analysis, and topology. The key point here is equivalent to the axiom of choice, to the well-ordering theorem. Equivalence. The theorem equivalence of the well-ordering principle of choice and Zorn's lemma are mathematically equivalent. This means that if it is assured to be the others, then it can be proven to be true as well. Non-constructive nature. The existing proofs. All three principles are used to prove the existence of elements or sets without necessarily providing constructive method to find them. This non-constructive aspect has been a source of philosophical debate. Venn diagram. The show to overlap the equivalence of well-ordering principle and axiom of choice in Zorn's lemma use distinct colors to highlight each other's principle and the areas where they intersect. This diagram is illustrative, showing the flow of logic proving the equivalence of three principles. The well-ordering principle, every non-empty subset of n has the smallest element proof. The fact that we cannot prove the principle of well-ordering with just the familiar properties and natural numbers satisfy under the condition of multiplication. Hence, we shall regard the principle of well-ordering as an axiom. Interestingly enough, it turns out that the principle of mathematical induction and the principle of well-ordering are logically equivalent. This means if you accept one as an axiom, you can use to prove the other. The principle of mathematical induction holds only if the well-ordering principle holds. Suppose there's S, a non-empty subset of natural numbers that has no smallest element. Let R x belongs to n, x is greater than S is greater than x for every S belongs to the natural numbers, and S is a set of natural numbers. Since S does not have the smallest element in the clear, that R and S is not. So it is obvious that 1 belongs to R and K belongs to R. Then any natural number less or equal to K must also be less than or equal to S for every S belongs to the natural number. Hence, 1, 2, K belongs to R because R and S are not. If we find 1 and 2, if we then find k plus 1 have been the smallest number, this contradiction shows that k plus 1 belongs to R. Therefore, the principle of mathematical induction has been implied R is equal to n, and then it would make an S as a non-empty set, which contradicts the assumption of S is non-empty. For every one that belongs to S and for every one k is greater than 1, if k belongs to S, that is natural numbers, then k plus 1 also belongs to the natural number. That's how we come to the conclusion. If k belongs to the set of natural numbers, then k plus 1 also belongs to the set of natural numbers. If the set of real numbers is said to be well ordered if every non-empty subset of T has the smallest element. Therefore, according to the principle of well ordering, N is well ordered. Example 3.7. Okay, so this is an example. Show that Q is not well ordered. Solution: suppose X is the smallest element in Q. Then x minus 1 is a rational number that is smaller than x, which contradicts the minimality of x. This shows that Q does not have the smallest element, therefore Q is not well ordered. We had to show that Q is not well ordered, so in the solution we say that x minus 1 is a rational number, that is, it is smaller than x, which contradicts the minimality of x. This shows that Q does not have the smallest element. Q is not well ordered. Thank you.